Hi, the section 7.3, the hierarchical or nested responses. So this is just an application of the multinomial regression model. And suppose that the response variable is categorical and has nested structure. So here is one example. So this is the diagram for the data for the malfunction on CNS. CNS is the inherent disease for babies. So the entire population of babies is divided into the no CNS. The CNS is the central nervous system, no CNS babies, and the CNS babies. And the majority is the no CNS baby. And out of CNS babies, we have the three types, the AN and the SP and other. So one way to apply the multinomial, the logistic model is to use these four categories, but often it's at first more important to see whether or not the baby has the CNS. Then after that, we just separate the CNS into three cases. So here that we will do the step one, we separate the no CNS group and the CNS group by binomial regression. Then after that, we divide this CNS group into three. Then we use multinomial, the logistic model. So here is an example, so sample data. So we have the count of babies here. So no CNS and AN and SP and other. So we have just four categories, but we have CNS, that is the summation of AN and SP and others. So at first, we want to compare the no CNS and the CNS. Under which condition that we have more CNS? We would like to see that. And the area, basically we have the two variables, the area and the work. So these are the predictor variable. So okay, so the yellow, so yellow is the response variable, and this is the predictor variable. And the water is also the predictor variable, but basically the area and the water are the same. So water is a numeric version of area. So just we have some numeric variable that corresponds to each area. Work is the parent's the job, manual job and the non-manual job. So we have only two categories. And this is the entire data. So we only have the 16 lines, but each line includes multiple observations, actually maybe from 1,000 to 13,000. So we have a lot of data. So we want to fit this response variable on either area and work or water and work, or just one variable. Yeah, so at first we define the CNS as the summation of AN, SP, and other. Then we make a plot. So this is the logistic regression. So we think about just the ratio of the no CNS and the CNS. And after that, maybe we can take the logarithm, but we just make a plot of the ratio of no CNS to CNS and each of the predictors. Then we can make this. Yeah, so you can see that actually the water have only 8 levels. So this and this have the same level. This and this has the same level. So actually we only have eight levels. Yeah, and this is the area. So this is just categorical, so that we make the box plots, and this is work, only two categories, so box plot. So you can see that at least the manual and the non-manual, so these have significant difference, it looks. And also possibly the water and the ratio of CNS to CNS is positive, possibly. Area, the between areas, maybe that we have difference because these are both small and both large. So it may matter. So maybe possibly it's better to consider just the area as categorical rather than to make it numeric as water. So now that we do the binomial regression. So remember that if we have two columns and each column represents counts, then we can fit the logistic regression model. And the first one is area and work, and the second one is the water and work. So the water and work is just the numeric version. So water is the numeric version of area. So we cannot add the three variables as a predictors because the area and water are basically the same variable. So I haven't shown the each coefficient, but this is the ANOVA table for each regression. So GLMAW, so first regression model, we have this ANOVA table. So this is null deviance. So if we don't have any predictor, so basically we regress the y on maybe I would say probability, the proportion of probability on just mu. And the second one is the same one, but the mu plus area, so area. Area, maybe area I. Then the third one is the mu plus the area plus work. So area, that we have the 8 areas. So we have the 7 additional variables. So DF is 7. Work is basically binary. So manual or non-manual. So we only have 1 degrees of freedom. Then we can get the residual deviance, that is the negative 2 times the log likelihood. So the smaller is better. So you can see that, for example, from null model to next model, the mu plus area, we have the increase of 7 degrees of freedom, and we have the increase of maybe 24.5. So you can see that the 24.5 should follow. I mean, 24.5 is a realization of chi-square random variable with DF7. So probably it's significant because chi-square 7 has the mean of 7, expectation of 7. So 24.5 is pretty large. And to compare this model to the full model, then we get the decrease of 13.5 maybe, and only 1 increase in degrees of freedom. So probably if we include work, then the model is better. And we have the same thing here. And still the pretty large improvement in residual deviance and only 1 parameter each. So it looks both variables are useful to predict whether babies have CNS. Yeah, so this is the comparison between these two. So water plus work or area plus work. So these models are not nested, but the deviance test, the difference of the negative 2 times log likelihood follows chi-square. So that is always true, even the 2 models are not nested. So usually to compare 2 models, the one is the F test. The one is the the negative, so the log likelihood ratio test. So this follows chi-square and F distribution. So this follows some distribution with some certain number of degrees of freedom. And this is valid for only nested model. But the difference between the negative 2 times log likelihood. That always follows chi-square distribution with the difference in degrees of freedom, df large minus df small. So we can compare by using chi-square distribution, and we can test. And actually, the area is categorical variable. We have 8 categories, that is 7 variables. Water is just 1 variable. So we have increase of 6 degrees of freedom here. Or actually, here it says the 13. So in total, 16 observations. So model 1 have 3 parameters: coefficient, intercept, and coefficient of water, and coefficient for their work. Work is binary. So the 16 minus 3, so that is 13. And this is 7 is actually the 16 minus 9. 7 plus 1 plus intercept, so that is 9. So increase in degrees of freedom is 6, and the decrease in deviance is 9.2. So this follows chi-square 2, chi-square 6, 6, and the p-value is 0.1581. So that means the next, the model 2. Model 2 has more parameters, but not significantly better. So probably it's enough to put water. At least it's not significant even if we use area as categorical variable. Yep. So now that we go on to the next one. So how to distinguish AN, SP, and other. And here it's slightly new code. So we still do the multinomial, the logistic regression. But why? Response variable is indicated by the matrix of the 3 columns. So these are numbers such as 5, 10, and 3, or 0, 0, 20, and so on. So multinomial random variable, that we have the multiple possible categories, and if we make a matrix whose columns are the numbers for each category, then we can fit this with the multinomial function. So it's similar to logistic regression and binomial regression, but here we have more than 2 columns. Then response are the predictor variable. Then you can see that the coefficient here, so that can be interpreted as, for example, this way. So we compare the 3 groups, and the AN is the baseline. So R set the baseline as the 1 with the alphabetically the first one. So you can change the level function to change the order. But okay, so AN is the baseline. So basically our models the log of probability of SP over probability of AN. And the next one, actually the log of probability of other over probability of AN. Then that is this. So these coefficients are obtained by this line. So you can see the how the coefficients are calculated. And also standard deviations are reported here. So you can see that, for example, this one, 0.11, but the standard deviation is 0.2, so it's not really significant. And actually, you can see probably all of the coefficients, except for intercept, are significant. So probably the model isn't really useful. Yeah, and we can use the step function. Still, it's the same as the linear regression. Step function to do model selection by backward deletion or forward selection by AIC criterion, because these models can calculate the likelihood, so AIC. So we can compare it. But actually, as we can imagine from this regression output, no predictors, the water or work manual, are significant and not useful for prediction either. So the null model is selected by AIC. So the implication is it's hard to distinguish AN and SP and other. So in the first step of the analysis, that we can distinguish the no CNS and the CNS. So that is good, but if we try to separate AN, SP, and other, then it does not work. So it makes sense to separate it into 2 steps. So first step works well. Second step doesn't work well. So it's clear that second step is difficult. And also, if we do just the 4 categories, if we use 4 categories, the no CNS and AN, SP, and other, then probably it does not work, because originally it's too hard to categorize the 3 CNS categories. Yep. So this is an example for the hierarchical or nested responses.